We identified a couple of caveats of the procedure that we have developed so far. One was that we were needing different shape functions for different elements of the same overall domain. And second, that each element integration for the K matrix or for the F vector required different integration limits. So this issue is solved very elegantly by using the something called a reference element. And then using the usual coordinate transformation rules of calculus. Okay, so let us look at this a little closely. This we are calling the element view of the finite element computations. So our objective is that we will define a reference element with respect to the real element. Okay. So if we pick any real element, let's say omega e, which is between nodes A and B and lying between coordinates x1 and x2, and these are real coordinates. And by real, what we mean is that this is the physical space where the body being analyzed is actually lying. And we define a reference element in something called a reference space or a reference coordinate space, which in this case we are denoting by the Greek letter psi. So this lies between node 1 and 2, and we say that node 1 will always have a coordinate psi equal to -1 and node 2 will always have a coordinate psi equal to +1. So basically this element, the reference element, always lies between psi equal to -1 and psi equal to +1, whereas the real element lies between coordinates x1, x2 or x2, x3 or whatever in the real space. Okay. Now in this setting, we define the shape functions in the reference element. Okay. So if we restrict ourselves to linear functions, so as of now, and we will do nonlinear functions later, but for now let us restrict ourselves to linear functions, and we make use of the properties of Kronecker delta and partition of unity. Then it is easy to define functions in the reference space as n1 of psi being 1 minus psi by 2 and n2 of psi being 1 plus psi by 2. So essentially we are looking at a coordinate transformation between psi and x. So we need a way where we can go back and forth between these two. So basically if we are given an x value, we should be able to calculate what is the corresponding psi value. And conversely, if we are given a psi value, we need to know what is the corresponding x value. Now one way of doing that is we can use the same set of shape functions that we have defined here. Okay, so you may notice that let's say for field interpolation, if we know d1 and d2, which are the nodal values of the field u, right? So this we will define as n1 n2 times d1 d2, where n1 and n2 are defined like this. Okay, so similarly we know the nodal coordinates x1 and x2. We can use the same n1 and n2, and we can define this x as a function of psi. Okay, so we have just from here we have done some simplification where x2 minus x1 we are saying is the length of the element Le. So once we have defined x as a function of psi, we can also define dx by d psi, which comes out to be Le by 2, and we can also define the inverse derivative d psi by dx, which is 2 by Le. And you can recall from your earlier calculus course that this dx by d psi in the multivariable calculus coordinate transformation is called the Jacobian or J of coordinate transformation, and this inverse is the inverse of the Jacobian. Okay, and also that the determinant of the Jacobian is usually denoted by small letter j, and in this case, since this is 1D, the J matrix and its determinant are the same. Okay, so this is what we were saying earlier, that the field interpolation u as a function of psi can be done using this n1 and n2 and d1 and d2, so as n of psi times de. But in the weak form, we will need derivatives u comma x. So basically, we will need derivatives of u with respect to x. But we know u as a function of psi. So what we will have to do is to use the chain derivative. We will say u comma x is u comma psi times psi comma x. Okay, now this u comma psi is n comma psi times d e, and the psi comma x is the inverse Jacobian 1 by j. So basically u comma x becomes n comma psi times de times 2 by le, and this u comma x, using the earlier generalized notation, we will write as b times de. Okay, where b is a vector in this case defined as this. So b is a 1 by 2 vector. Okay, now the integrations can also be converted. So an integration in x, which is from x1 to x2, basically this is the element integration, can be now converted into psi space, where x can be written as a function of psi, and this dx becomes j times d psi. Okay, and once we convert it to the psi space, the limits will become minus 1 to 1. Okay, so basically this integral becomes like this, and now the advantage of doing this or defining this reference element and then making use of the coordinate transformation is that now that shape functions will be same for all elements. Okay, so shape functions of n1 equal to 1 minus psi by 2 and n2 is equal to 1 plus psi by 2, these will not change from element to element because we have defined a reference element which will not change. The only thing that will change is the mapping, and that mapping properties we have defined earlier using the Jacobian. Another advantage is that integrations will now always be from minus 1 to 1. Because this reference element is defined from minus 1 to 1, the integrations will not change the limits. Okay. Now one last thing which we need to discuss before we can start programming the 1D finite element method is numerical integration. So although the problems we have done so far, in those it is possible to do or carry out analytical integrations. But in reality, in practical problems, these analytical integrations will not be possible. And of course, they will also not be friendly for programming. So we need to know how to do a numerical integration of the things that we have.